Hi viewers, I'm back with another exciting problem from GATE. So this is regarding vibration isolation. Again, it seems like a really simple problem, but unless you know the concepts really well, you won't be able to answer this question correctly. So pause the video, try to solve this particular question on your own, and then come back and see the whole video. In this particular problem, they are talking about isolation transmissibility. So since they are not explicitly telling it is displacement transmissibility or whether it is force transmissibility, let's think or let's assume they are talking about displacement transmissibility, and mostly that is the case. If in a question paper they are simply talking about transmissibility, then they are referring to displacement transmissibility. Well, so this is the mathematical model that we have, in which there is a base excitation. Base excitation is harmonic. My base is exciting with an amplitude of capital A and frequency little omega. Then my response will be having a shape like this, or a mathematical description like this, where this is the amplitude, and then we define the displacement transmissibility like this, which tells you which is the ratio of the response amplitude to that of the excitation amplitude, where zeta is the damping ratio and r is the ratio of frequencies. I have shown a detailed derivation of this particular expression in my earlier videos, so I won't be repeating the same here. You can always go back and see those videos to know how these equations are arrived at and what are the assumptions that goes into into deriving these equations. Okay, now to give a better idea of the behavior of the system, since the system is subjected to a harmonic excitation, it is always to look at things from a frequency domain, because from a time domain you won't see anything interesting, because the response is also harmonic, so you will just see the same kind of stuff repeating time after time, or after a regular time, which is ineffective, called the time period of the response. I won't get into the details, so let's plot the displacement transmissibility with respect to frequency. Here you can see a few observations. When you have a very small value of little r, or omega by omega n, your displacement transmissibility is around the value 1. And moreover, you can see when you have damping helps. Damping brings down the displacement transmissibility values in this regime. In this regime, I mean for values less than omega by omega, for values of omega by omega n which is less than root 2, because this point is where we have omega by omega n equal to root 2, or r equal to root 2. So in this regime, obviously your displacement transmissibilities are coming down, but in this particular regime, that's not the case. This is the curve for zeta equal to 1. So in this particular regime, for zeta equal to 1, we have the maximum displacement transmissibility value. So bringing down the zeta value may not help always. It depends upon where you are operating, whether you are operating to the right side of this particular line or to the left of this particular line. So that cannot be generalized. The other thing, why all curves meet at a value of 1 when omega by omega n equal to root 2, that can be simply explained because we had an expression for displacement transmissibility like this: 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. If you Have a look at the denominator. When r is equal to root 2, what happens is that this particular denominator will be minus 1 whole square, which is just 1, plus 2 zeta r whole square. So the denominator and numerator becomes the same, so we will have a value of 1 for the displacement transmissibility irrespective of the amount of damping present in the system. That's why you see all these curves meeting at this particular point. So I think that's it. That's what all I have to tell you about this curves for displacement transmissibility for different values of zeta and for different values of little r, which is the frequency ratio. Now let's go back and answer the question. The first option says T is nearly unity at small excitation frequencies. Makes sense. We just saw that. Then the second statement is that T can be always reduced by using higher damping at any excitation frequency. That is wrong. This is only true when your excitation frequency omega is less than root 2 times omega n. The B statement is only true in this particular regime. It is not true once you cross that particular value, when your excitation frequency is greater than root 2 times of the natural frequency. And then they are saying T is unity at the frequency ratio of 2. Makes sense. We just saw that. Then T is infinity at resonance for undamped systems. It is infinity because that can be explained in a lot of ways. Let me write the formula for displacement transmissibility once again. This is the numerator and the denominator goes like this: 1 minus r square whole square plus 2 zeta r whole square. Since that is an undamped system, these two terms will cancel off to 0, and here you have an r equal to 1 for the resonance condition. So that means you have something like of this sort, 1 by 0, because zeta is 0, this is 0 because you have an zeta is 0 because you have an undamped system, and r equal to 1 because your system is at resonance, which effectively makes the displacement transmissibility to assume a value of infinity. So this is a very good question. So the wrong statement is the B statement. You can only answer this question if you clearly know the whole concept of vibration isolation, and if you know that curve really well. It's a nice question. So thanks for watching.